So in this video, we'll discuss about another graph theory paradigm, which is random walk. Now, what is a random walk? A random walk is simple graph traversing done randomly. That is, we choose the neighboring vertex at random, and we go on till we have a termination condition. And that termination condition can be a time that we set for traversal or maximum iterations. Like we want only to go through 30 nodes, so we set the maximum iteration as 30. Now, in this video, we'll discuss about random walks using implementing random walks using GraphX, which is Apache Spark library, and Peggle, which is a library provided by Google, sort of message passing library, which makes the graph computations much easier. So let's start with the presentation. So first we'll discuss about the overview or the problem statement of the project and the proposed solution, which is the graphics and the Pregel library. Then we'll discuss about the meaty part, which is the Pregel algorithm and how does it work, and also some future enhancements. Right. So talking about this project, like the goal of the project is to perform parallel random walks. So the random walks or the graph traversals that are happening on the graphs should be parallelized, and at the same time, we should avoid having redundant walks. Now, what is a redundant walk? It's a walk where you repeat the paths. So we don't want to repeat the paths simply to avoid those redundancy, and the computations will also be saved. Now, once those random walks are completed, we will perform similarity with another graph, which is a requirement of this project. So this is about all about what is the goal of this project. Now, moving on to the proposed solution. As we discussed, like we will use Spark's graphics library and Google's Pregel library to perform these random walks. So Apache Spark basically works on the concept of RDDs, which is resilient data sets, and you have the graphs distributed as part of those RDDs. So what do I mean by that? Like, so a single RDD will be computed for a vertex and one for the edge. So your edges and vertices will be stored as RDDs, and Spark's Apache library will automatically distribute these vertices and edges as part of those RDDs into different computing clusters. So the operations that you perform on these graphs will be distributed, and you would be agnostic of that fact. So that is taken care of by the Apache Spark. So now moving on to Google's Pregel library. So this is the library we are using to actually do the random walk. Now, Google's Pregel library works on the concept of message passing. So you give an input graph, you set you select a set of vertices or initial state. Now those starting vertices will have state X, and the rest of the vertex will have state Y. Now since you have selected those vertices, you can move to their neighboring vertex as the next iteration. And the next that iteration step is basically a super step in Pregel. So what happens at that super step? At a super step, your existing vertices, if you pick any vertex, that vertex can perform the message, take in the message that was performed by the earlier super step, and compute its state accordingly, and also send the message to the neighboring vertex, and which will be computed as part of the next super step. So this is a diagram which helps you understand of the flow of the Peckel algorithm. It basically consists of three major parts, which is the program that is executed by each vertex, the message sender, which is the message that you want to send from the vertex, and the message combiner, basically aggregating those messages which are received, let's say, from multiple vertices to that single vertex. So we use random walk in using Pregel in such a way where you have the starting vertices, you have the starting vertices, and you store the vertex ID in the initial state. So signifying that you have traversed that vertex ID. So you already have that stored in the data structure. Then as you move along, you keep on adding those vertices to that data structure. And this is done for all the nodes. So we traverse through all the nodes in the graph in a parallel fashion, as Apache Spark will take care of they take care of distributing these input graphs into RDDs, and this computation will be done in a distributed fashion. Right. So we'll move on to the demo. I'll walk through the code that was implemented for this. Um, so this is the code. And let's go to the main function. Right? So it's a very small function, and it simply calls the random walker class post loading the graph as a GraphX library. Right? So going to the random walker, first we'll see what happens. Now we call the Spark libraries, which is Spark context, Spark con, just to initialize the Spark environment. Then we move on to the graph load function. So this is a graph loader. I'll quickly go through the working of this function. So what it does is basically take a take a list of nodes and edges and returns them, basically deserializes those nodes and edges from a file and returns this as a list of vertices and the edges. Now, once you have the list with you, what you can do is create the RDDs from those vertices. So this is the code for that. What you do is basically have RDDs for the vertex and RDDs for the edges. Now, talking about the vertex, it's slightly nuanced in the sense where you have the starting vertices which are chosen at random. And for those starting vertices, you already have the ID added to the list of the data structure that I talked about. In this case, which is the list, you already have traversed that ID. So hence, you have ID added to that data structure. Now, moving on, we create that graph using vertex RDDs and edge RDDs, and you pass in that graph in the Pregel call. So graphics already has a Pregel method which takes in the initial message. The initial message, this message will be sent to all the vertices. And in this case, we are simply passing the empty list and from which will store the path of your random box and the vertex ID to each of the vertices. Now, the next part is the maximum iteration. So this is the maximum number of nodes that you want to traverse per random block. And the next is the direction. So how do we want to traverse? So edge direction dot out, the method is the meaning where you have the traversal going through the edges, going through the outgoing edges. So you can have a direction dot both, which means you can traverse for both incoming and outgoing edges, or just the incoming edges as well. In our use case, we are using direction dot out, which is also the default value. Now you have um, three important components, which is vertex program, send message, and the message combiner. Now vertex program, going to that vertex program, we see that this vertex program is executed for all the vertices. So it takes in a bunch of arguments like the node ID, the vertex data that you want to keep as part of those RDDs, and the message that is sent as part of those outgoing edges. So what it does is basically increments the message with the node ID and also the matcher value. So we'll talk about matcher in the later part of the video. But for now, this vertex program is computed for all the vertices, and it basically increments the attribute which stores the path with the incoming vertex. Right. So next is send message. So send message is pretty simple. If you want to store the paths, you want the message to contain the path or the vertex ID which is already traversed. So as part of one iteration, the send message will compute or add the vertex ID of the previous iteration, signifying that you have already traversed the vertex ID, and also taken the vertex of the current processed vertex. Right. So message combiner is nothing but a way you want to combine those messages which is received in case where you have a single vertex receiving multiple messages. So how do we want to sort that? So in this case, we are choosing the message which is having the largest or the longest length. So that message is chosen, right? So this computes our Pregel algorithm. Uh, and basically, once the Pregel algorithm is done, once those computations are completed, you have the result graph. And from that result graph, we'll take out those values of the random walks and further make computation and decisions on top of it. Right. So this was all about the project itself. Now, as part of this project, what we can also do is deploy it in a AWS cluster, AWS Spark cluster. So let's move on to that. Right. So I have my AWS console already logged in. In order to deploy my application into a Spark cluster, first I need to do is take a jar of my file. So I have the steps in the GitHub repository on how to create that jar. So you can refer to that. But I'll go to just show you how the jar is stored in the S3 bucket. Now, so this is the jar path. It already contains my program's jar, and also there is these deserialized files, or serialized files rather, which contains your graph, uh, both the original graph and the graph which is modified, right? So these are the files which is taken into account by our program. Now, moving on to the EMR part. Now, how do you deploy a cluster? So what I'll do is go on create cluster, select my name of the cluster. I'll select random rock, and choose the existing, which is the latest. This is the latest cluster. Just choose this. Remove all the other dependencies that is not required. So, and you have the Spark 3.4 one selected, right? So keep the existing configuration as is. You can change this according to your need. I'll choose the instance type of my nodes on which the Spark program will run. So I'll select info.large for all of them. I'll keep the settings as default. I already have a VPC and subnet created. I'll add a step here, which is the custom jar. So I'll select the S3 URI of my custom jar. Um, Name it random jar, jar location, and terminate the cluster if it fails. So save step. I keep the configuration as default. IAM role. So I've already created an IAM role, which is easy to EMR. And once confirmed that all the configurations are there, I'll click on the create cluster. Now, this will take around 10 to 15 minutes. You need to wait for the cluster to complete. Once the cluster completes, we'll go through the output and how did it compute our Spark program. All right. So now we can see that after around 10 minutes or 15 minutes, our cluster is completed, or the step that we added to the cluster is completed. Now let us see the log files and standard output of this step. So first, let's open the log file. Here you can see the Spark version is 3.4.1, and it's starting your Pregel application, which was added as part of our program. So it's the same Pregel application. that we added as part of the sc.conf file. So in the logs, here we can see different ways log steps. In the sense we have the RDDs, the each superstep that is executed by the Pregel function, and the messages that are passed. So if you go at the end of the log file, you'll see that the random walks were created, and uh, the output of the random walks can be seen in the output log, which is here. So here you can see the different random walks. So this is the file which stores the log of random walks, and uh, basically the colon and the brackets is reflecting the matched ID. So in this project, what we were supposed to do is basically, as part of the random walks, for each node in a random walk, compare it to another graph and calculate the similarity. So this colon represents nothing but the node ID of the compared graph and the similarity score that is done through Jacquard index. So this is 300 um, node graph, which has multiple random walks being computed, and this is the output for that. So once you have those outputs generated, we have another program which is attack handler. So based on the similarity, we attack on those nodes if it has a higher similarity. All these details are mentioned in the README file of the GitHub repo. So I'll link that, and so make sure you check that. And I'll also add some more links regarding Apache Spark and Plagal, which will help you understand more about this project. Yeah, so that was all for this video. Thank you.